Good morning, I am Fan Wei. In this work was done with my advisor, Professor Cha-Ping Chen, and today I will going to talk about how retrieval augmented diffusion can help speed defect detection generalize better to unseen attack. And here is my outline. And then first of all, I'm going to introduce the introduction and my motivation. And next, I will introduce my sports speed detection system. And finally is our conclusion. And first is my introduction and motivation. As we know, speed defect detection has become increasingly important due to the rapid progress of text-to-speech and voice conversation technology. In real-world signal, detectors often face full method to and channel condition that we'll never see during training. An ASV spoof file check 1 is designed to reflect this challenge. The test data includes unseen spoofing attack and transmission channel. Under this setting, models that rely purely on discriminated classification struggle to generalize. The lows, self-supervised front-end such as WebLM, provide strong acoustic representation. Classifiers train on them and tend to overfit attack suspicious artifacts and perform poorly on unseen spoof methods. A recent study attempts to improve generalization using data augmentation in sample learning or attention-based pooling. But however, this approach remains fundamentally discriminative and do not especially model the distributional difference between genuine and spoof speech. And motivated by this, we propose a retrieval augmented diffusion framework that introduces class-away generative period. Our key idea is simple. A genuine sample should be reconstructed well when a condition on a genuine prototype, but poorly under the spoof condition, and vice versa. This reconstruction asymmetry produces an energy gap and provide a complementary and integral signal for defect detection. And next, I'm going to talk about my experiment data set. And this table summarizes the data set used in our experiment. For training, we combine bonafide and spoof sample for ASV5 and ASV 2019, which provide diverse spoofing conditions. The evaluation is conducted on ASV5 test set, which contain a large number of unseen spoof attacks. Overall, the data set are highly imbalanced, reflecting the realist defect detection scenario. And next, I'm going to introduce our spoof speed detection system. First of all is the front-end system. And now I'm going to introduce our front-end system WebLM with multi-head factorized attention. We start from the 12 hidden layer of WebLM, each with the shape T by F tensor. And these layers are stacked and rearranged into T by L and I by F tensor. So for each time frame, we can preserve information for all layers. And next, the features are projected from key and value tensor with the shape T by L and by C, and where C is compressed feature dimension. And we then apply 32 attention head to the value feature, producing attention weight to the shape T by L by H tensor. And by multiplying the attention weight with the value and summary over time, we attempt a time weight feature for each head with the shape L by H and by C. And the output from the all head are concat from L by H multiply C, and we average over the layer dimension L to produce a growth representation B by H multiply C. And finally, the vector is projected to 25-dimension embedding, which is fit into the classifier. And next, we will fine-tune the WebLM by layer-wise learning rate decay. Here we apply layer-wise learning rate decay when fine-tune a WebLM. The top layer with the large learning rate, when the lower layer will yield progressive small one. This allows the model to adapt test the specific feature in higher layer, while preserving general exhaustive knowledge in the lower layer. In our setup, the learning rate is decayed by 0.95 for each lower layer. And next is our RAD and diffusion system. And first of all, the input feature X, which is generalized by WebLM, is used to query two separate knowledge bases, one for bona fide speech and one for spoof speech. And for each knowledge base, we retrieve the top 5 more similar features. These retrieved features are then fed into the diffusion conductor in two ways. The first pass computes a weighted average of the 5 retrieval features with a time-preserving input, forming a single representation vector. The second pass keeps all the five retrieved features and use them together with the time preserving input feature to compute a local condition. And especially X-Prong attempts to retrieve features through cross-attention, followed by the linear layer and reloop, to producing the frame level condition Z local. At the same time, the weighted average prototype is combined with the outrank level input representation from a global condition vector Z global, which summarizes the sentence level information. These local and global conditions are then used to guide the different models during the reconstruction. And next is about our diffusion system. This figure shows how our diffusion-based energy signal is computed. We start from the original speed feature X, and first add Gaussian noise to attempt a noise version xt following the standard diffusion process. The diffusion model then takes xt together with the diffusion step T and local condition and global condition, and use the denoiser DDIM. We reconstruct the speed feature twice, once under the bona fide condition, another is under the spoof condition, and each reconstruct feature is compared with the original axial cosine similarity will give our two energy value. Finally, we take the difference between these two energies to form an energy gap. This gap tells us whether the signal behaves more like bona fide or spoof speech, and is used as an additional decision proof. And in the training mode, if the input is spoof, it will be E bona fide minus E spoof, and then we expect to see that E gap is bigger than 0. If the input is bona fide, it will be E spoof minus E bona fide, and also we expect to see that E gap bigger than 0. So whether the label is bona fide or spoof, the model is expected to see that the E gap always bigger than 0. And next, I'm going to introduce our backend system. Here we combine two types of information for classification. First, we use WebLM with feature as the main representation. That is generalized by multi-head filterized attention. And second, we project the energy feature, bona fide energy, spoof energy, and then the gap through a linear layer. These features are concat and feed into the Fourier connector to predict a bona fide or spoof audio. And finally is our experimental result. This table shows the EER comparison across different models. The word-to-vector and WebLM resonate 18 baseline achieved at the EER of 9.28, and previous RAD model with SA resonate and grow performed the worst at 11.31, and our project RAD and MHFA with the diffusion improved in the EER to 9.17, and using Bio and LSTM backend further reduced the EER to 8.96, but with higher complexity and time. And finally is my conclusion. To conclude, we use retrieval for dual knowledge base together with a diffusion model to refine WebLM feature. This produces more fine-grained representation for anti-spoofing. As a result, the system can be better tell genuine speech from the spoof audio. With a lightweight, multi-head filterized attention backend, our method achieved a solid performance on SVU Check 1. And thank you for listening.